Clean, renewable energy has never been in greater demand than now. As the world transitions away from fossil fuels, tapping potential sources for renewable, environmentally friendly power has become of greater importance. Our project focuses on a new emerging form of renewable energy called flow-induced vibration energy harvesting. And our goal is to use sensor-based estimation and machine learning to control this and maximize the energy harvested. So what are flow-induced vibrations? Well, when a bluff body, such as the cylinder shown, is immersed in a moving fluid, this can cause oscillatory motion by the vortices that are shed off the back. This oscillatory motion can then be extracted, and this energy can be stored. To better understand the goal of our project, we must first discuss some of the previous work that's been done in this field. As mentioned, at certain speeds, the flow will induce these natural oscillating motions when a cylinder is placed within the flow. When the speed of the moving fluid is increased, however, there's a point where the cylinder no longer oscillates and becomes stationary. However, from previous research, it has been shown that placing another cylinder upstream of the primary cylinder, let's call this the secondary cylinder, allows for oscillations to continue at these higher water speeds. Currently, there has not been an investigation into the benefits of real-time control of the secondary cylinder. Our goal is to control this secondary cylinder and be able to move it in an optimal manner such that we can extract more energy from the system. So how exactly did we achieve this goal? Well, there are three components that are worth mentioning. The first, an actuator system that will physically move the secondary cylinder within the space. The second is a pressure array that will record the pressures at several locations within the moving fluid. And this will be sent to a prediction and control software that uses machine learning to decide the optimum position of the secondary cylinder, sending this information back to the actuator system to actuate it in real time. To fabricate these three systems, we needed to select components that would not only be functional to the tasks, but also easily interfaceable. For the actuator system, we constructed the frame from standard aluminum profiles. The motion of the cylinder is created using stepper motors and a belt system, which slides the cylinder along linear square rails. Onboard closed-loop control of the cylinder was implemented using standard microcontrollers, which were also used to read positional commands from the predictive control. For the sensor array system, wet pressure sensors were chosen as they give more direct and accurate pressure readings while in water. The connections between the wires and the sensors were waterproofed through layers of silicone conformal coating and heat shrink tubing. To amplify the pressure signals, a compact amplification system using in-amps was designed to permit for easily controlled gain via one resistor and quick connections to the sensors and DAC. This allowed for pressure changes as small as 0.03 pascals to be detected. A sensor housing array was designed and 3D printed for quicker prototyping. It has 7 sensing locations horizontally and 3 vertically, allowing for the customization of sensing configurations. For the prediction and control, we opted to use Python with PyTorch to create a neural network and implemented the predictive control system in C++. The control system that was designed was a model predictive control system. This was chosen over a standard PID control system as it had predictive capabilities that would allow us to determine the optimal placement of the cylinder in real time. So what does our final design look like? Here we can clearly see the primary cylinder in black and the secondary cylinder, which can be actuated, in gray. Here we see the pressure array on the left side of the water channel. In this video, you can see that the secondary cylinder, which is the silver cylinder, is stationary while the primary cylinder is oscillating due to flow-induced vibrations. Note that at these higher velocities, As previously mentioned, the primary cylinder will not oscillate unless the secondary cylinder is present. With the secondary cylinder being mounted to the actuator system, we are able to control its motion and move it such that we can amplify the motions of the primary cylinder. It can be seen in this motion that the primary cylinder is leading the secondary cylinder and moving at the same frequency. The oscillatory motion of the secondary controlled cylinder is very important. In this video, you can see a very similar motion to the previous video. However, now the primary cylinder is not oscillating at all. The difference in these two oscillatory frequencies was found to only be 0.2 Hz. Based on our optimization of the secondary cylinder's motion, we are able to achieve up to 25% increase in lift force on the primary cylinder as compared to a stationary secondary cylinder. This measured increase in the lift force could theoretically be extracted to create more energy. Additionally, we have shown that the frequency of oscillations of the secondary cylinder is essential and must match the natural frequency of the primary cylinder to increase the amount of energy that could be extracted. In future research, it would be desirable to see how much we can scale this up and what power potential we could get out of this.